So in this video, we will be modeling the temperature profile of a bar using explicit differencing. So as you can see here, I have the bar drawn where we have left bound temperature of 50 degrees Celsius and a right bound temperature of 80 degrees Celsius. And we also need to consider that our Q there's no heat loss or heat generated in this problem. And again, our goal is to be getting a temperature profile, so that profile is going to be dependent on the position in our bar and then also the time as well. And we will be looking for a linear line or a steady state for this temperature. So as you can see here, I've started out with our heat diffusion equation that we found in the last video. Again, I disregarded the part with Q since our Q is 0, and then I just multiplied omega over to the other side. So now what we're going to want to do starting off is we're going to want to approximate these two partial derivatives. So how we're going to do that is we're going to have to look at small increments of time and position, and we'll just call those delta t and delta x respectively. So our time step and then position, change of position. And then we will also need an index for how many of these like time steps and change in position we're doing. So for position, we can just call it something like j. And j is just going to be a list of integers, right? Like 0, 1, 2, and that's going to be each step in position. And then we can do the same thing for time, and we'll just call that like n. And again, it will just be integers like 0, 1, 2, and so on. So that means that our x and t respectively in this equation, our t is going to be equal to n times delta t, and then our x is going to be equal to j times delta x. So now we can start our explicit differencing. So we're going to start off with the harder one, the second partial derivative of the temperature over position. But we're going to start off just doing the first derivative. And that will, obviously the bottom will just be our delta x, our change in the x, or position that we're using. And then the top will be the temperature at our like previous position at a given time, and then minus temperature at the position we're looking for at time. So again, if we kind of represent that up here, it's like if we split this up and had this as like position j minus 1, position j plus 1, and we're getting that right there as our delta x. This should be j plus 1 actually, because obviously we want this to be larger than this if we are subtracting them to get the partial derivative. So now we are going to get the second partial derivative, and how we're going to do that is by getting the difference between the first partial derivative. So again, we're going to be doing difference, and again it will be over delta x, but this time instead of going one position in front of where we are, we're going to be going one position before. So we will have t sub j comma n minus t sub j minus 1 comma n. And again, what this is doing is getting a difference between two of the, let me put the squared there and squared there, two of the first partial derivative of temperature with respect to position. And again, all this is going to be over delta x again. And now what we can do is we can combine like terms. We have two of these t sub j comma n's. So if we just simplify that out, I'm actually just going to erase this whole thing. We'll have t j plus 1 comma n minus 2 t sub j comma n minus t j minus 1 comma n, and then all over delta x squared. So before I move on, I did have a little mistake here. This will actually be plus, because again, we were subtracting a negative, because we were subtracting those two first partial derivatives, and then we had that negative there, so it would actually be plus. And then, so now we can move on to this partial derivative, and it's going to be a lot simpler because again, it's not a second, it's just first partial derivative. So it's going to be a lot like our first partial derivative for this, but instead of position, we're going to be changing the time. So again, we'll have a temperature at position j, then this time we will be changing the time to n plus 1, and then subtracting from our t sub j comma n. And again, it'll be all over, but instead of this time delta x, now it will be over delta t. Delta t. So now we can rewrite these all together. So we will have first alpha. I think I might have called it omega earlier, but that is alpha. I hate the Greek alphabet. And then we'll have t sub j plus 1 n minus 2 t sub j comma n plus t sub j minus 1 n, and then delta x squared, and then all that is going to be equal to our other one that we found, t j comma n plus 1 minus t sub j comma n over delta t. And actually now what we can do is we can multiply delta t over to the other side, and we actually will get a constant that we can call r, and r is going to be equal to, again, alpha delta t over delta x squared. So again, once we multiply that over there, we'll get an r on this side. And then we're also going to want to add t sub j comma n to both sides as well. And what that will do is isolate our t sub j comma n plus 1 on its own side. And we'll end up with got here? T sub j, comma, n plus 1 equal to, and again we'll have that r, so we can distribute that out, and we'll have r t sub j plus 1, comma, n, and then minus, plus, and then we have we'll have 1 minus 2r, because again this r is only distributing out to these here, so we'll have 1 minus 2r, and then our t sub j comma n, and then also plus r, and then this here, our t sub j minus 1, comma, n. So this is our explicit differencing equation that we have found and that we will now use in our code. So now we're going to start to work on making a temperature profile plot for this bar. So as you can see here, we have imported numpy as np, and then from plotly.subplots we've imported make subplots. And then as you can see here, I have a bunch of constants that were given to us in the problem here. So first, the thermal diffusivity of 1 meter squared per second, and then our spatial increment of 1 meter right here, and then our time step of 0.5, and then we have an equation, or we have a variable relating all those, r, where we have this equation here, which we had on our board over here as well. And then we have the starting temperature, which is room temperature, 20 degrees Celsius. And then we have a left bound temperature of 50 degrees Celsius, which we had on our board as well. And a right bound temperature of 80 degrees Celsius, which is also on our board. And then also we have the length of the bar, which is given here of 20 meters. So now for our x-axis, we're going to want that to be the same length as our bar here, or however many position steps we're using for our R bar. So we can say that x will be equal to, and we can actually use the numpy.arange formula, and we're going to want it at length n. Like so. And I'm going to shift n around that. And then now for the temperature, we're going to want that to be the same length, like, as you can see here, shape like, we're going to want it to be the same length as that n length. But again, we're going to want it to start at t0. And then now we can also specify our left and right bounds. So we can just use Python indexing, which obviously it starts at 0 in Python. So our T0 for our left bound is going to be 50, or we'll just put it as TL. And then our right bound is going to be our TR. Like that. Now what we're going to need is a for loop calculating the temperature at different positions for the later time step. So what that's going to look like, so for I in range, and we can start at 1 because we already have our initial temperature here. And let's do about like 100 iterations. And we do need a colon there as well. So just before we were deriving, as you can see here, an equation for the temperature at the later time step based on temperatures at the earlier time step, but at different positions. So what that means is that we're going to have to slice this array here in Python And so how are we going to do that? So we're going to want all the values in between our initial value and the final value. So how we're going to do that is we're going to start from 1. Again, we don't need this initial value, we already have it as 50. And then we're going to go to the penultimate value. But for slicing purposes, we put -1. Again, our slicing is not going to include that final value since we already have it at 80. But that's just how you do the slicing in Python. And then that is going to equal this equation that we derived here on the whiteboard earlier. So now we can start to type this equation in. So to start off, we have R times, and this t value is at a position 1 greater. So that will be starting at 2 and then going to 0. And then our next one is just plus, and it's just our 1 minus 2 times R, and then that multiplied by t, and this will actually be the same slicing since it is also at position j here, so j to -1, and then plus, again it's R times, and this time it's -1 on the position, so it'll be zero here, so we can just put a colon, and then -2 for our time step, like that. So now we are going to use a conditional to determine how many plots we're actually going to make. So how we're going to do this is by using a module. So basically if we divide our I by a certain number, we'll get a remainder, and we're going to want that remainder to be 0. So we can use this thing called a module. So if we do like 30 and then it's actually the percent sign, 7, it's going to give us 2, which obviously is the remainder. 7 can go into 30 4 times, and then with a remainder of 2. So we can use that here, and we can do by 10, and if that equals 0, then we will plot it. So now we are ready to start making our plots. So now we can start off by making a plot of our initial time step temperatures. So we're going to go fig subplots, scatter, and then our x's are going to equal our x values from before, our y's are going to be our temperature array here, and then the mode is going to be lines, and then we can have a name or a legend where we can just use an f string and have a time corresponding to each temperature that we have out there. These parentheses, or I think that I had it right with the apostrophes. And then we do need parentheses here as well. Okay, and then now we can copy and paste this, or just the second part down here. Let me make sure this is right, yeah. So we will have to change this legend here. Instead of 0, we're going to want it to be our I times our time step dt. And then finally, we can update our layout. Update layout. And we're just going to specify the width and height. And let's see if we get a plot. So it says in here this float. Okay, so we just have to get rid of this decimal place here. And then run that again. And run this again. And we should get a plot here. Yep. So as you can see here, we never reach a steady state between our 50 and 80 up here. So we're going to want more iterations here. Let's do something like 400. And then we're also going to want this to change so we don't get too many plots. Let's go like 25. And let's see what this looks like. Yeah, so that looks a lot better with these straight lines between 50 and 80. And as you can see still, it is increasing with each line as well. So obviously this temperature profile is working for this time step. But if we increase this time step to, let's just say 0.508, and we're going to decrease these iterations to like 380. If we just do that, you can see our plot just goes completely crazy. And that just has to do with the stability. So even if we go even higher, like let's just go to like 0.6. And as you can see, these temperatures of 1 times 10 to the 52nd, that would never be true. So obviously something is wrong with our temperature profile and with the stability. So in the next video, that is going to be what we will investigate.